Oh, I guess I better put the screen on for you all.
Yeah.
The only reason your grade didn't show
That's
up,
not even just that, it's that. And then everything's just stressing me out.
I'll look it up. I'll tell you what it is. Don't worry.
Don't tell them front five, it's probably bad.
I wouldn't do that.
She's made a 70 on it, y'all.
I even have a problem with sending it as an email.
Because you're scared you'll send it to everybody.
No, I've never made that mistake. But I've always been afraid that it'll be seen somewhere because your emails forever.
So funny.
Yeah, I don't want to be in retirement 20 years from now and have somebody chasing me down for, you sent a grade to me 20 years ago.
Now everybody knows.
And everybody knows I failed that class, you know. Not that you do that, but you
Can't
know.
be as bad as what I'm doing to the kids think, so.
Statistics. It's just, yeah.
Yeah, it is.
Okay, let's get started. I guess, okay, I think everything is opened up. So let's go ahead and start. Anybody have any questions on anything today?
So you said we'll finish lecture Wednesday, so we should have, we'll take the exam for next week, right?
Yeah,
And then
yeah, it'll open up Wednesday and I'll leave it open until Sunday night.
when is that Wednesday?
Uh,
This week, next week?
This week. This is it.
Wait, so the final is gonna have to be this week too?
The finals next week.
When?
Yeah, final will be
we have
the
two
7th and
exams
last.
this week? So we have 4 and 5 to do, and then the final? 4
The
and 5?
finals
4 is
next,
done,
the,
right?
the final is next week. What, you know, I'm going to,
You
I'm,
shouldn't ask if anybody had any questions.
I
You really
intend-
shouldn't have.
I
I have so
intend,
many questions.
can I speak? I intend to open up the final next week towards the end of the week, so you have plenty of time to get ready for it. You know, the last lecture exam is a very short content. If you look at the slides, there are only 44 PowerPoints on respiration. That's not a lot of content. And I'm going to emphasize today what content you need to remember.
Okay.
They're called hints. Hints, okay?
Hints is test.
Yeah. Same thing. I'll do the same thing on Wednesday and maybe today if I ever get to it. That was not a comment. That was just an observation. I don't do snarky on Monday.
Please don't.
So, because everybody takes it serious if I do snarky on Monday. We'll probably get into into immune system today for a little bit. It's most of it is really interesting material. There's a couple things there that are really tedious, but the interesting stuff, particularly in light of what we've just gone through in the past 2 years, a lot of this will make, you know, it'll help you appreciate that more. So, okay. Now, comment here. Yes, I understand. It is crunch time. It's on both sides of the table, you know. I wake up in the middle of the night trying to figure out how I want to get everything done so that you all can cover the content on the final. Because remember, I don't make up the final. It's the final that you take the same final that everybody else does from every instructor. So, and I've tried to cover everything that the final will address, but I know that I've diverted into areas. I, like every other instructor, does that. If you find bizarre questions on the final, they're not mine. I'll just tell you that right now. So.
One quick question. Can we do Wednesday live for a final exam review?
There's a thought.
Because we're not gonna have.
That's
to
a great
That's
I'll be. I'll come.
Okay. Yeah, that's a good idea. I'll send out an email to everybody, let everybody know from both labs too, and as a reminder. But if that, I've just had a suggestion to do the final exam review on Wednesday afternoon. I think that is a great idea.
You're welcome.
Yes. So, okay. Let's,
Probably recorded, right?
of course, and then
Oh, good lord.
and then post it so you can watch it again and again and again. So,
Yeah.
you know, if you ever have trouble sleeping at night, just start watching my videos. Right now. So, okay, let's get started now with. Let me. Nice if I press the share screen first. You know, you all probably let me go for a half an hour before you told me. So, okay, now we are on this. Okay. We're talking about breathing in and out of the lungs. Now, I know this is the last topic I talked about on Wednesday, and it can be pretty confusing. Basically, our lungs set inside the chest. There's air inside the lungs right now. In the thoracic cavity, we have our lungs with air. There's air inside the lungs. Now, sometimes that pressure inside the lungs is greater than the outside, and sometimes it's less than the outside air. There's pressure. We call this the intrapulmonary pressure. That's the air inside the lungs. When we exhale, the pressure drops. When we inhale, the pressure rises. There's also pressure pushing against the lungs from the cavity. Now, remember that our lungs are covered with the visceral pleura. That's that goopy surface layer that sticks to the surface of the lungs, and there's another goopy layer that sticks to the inside of the thoracic cavity, and in between we have serous fluid, so there's no friction when our lungs move. Well, there's pressure in that space between the visceral and the parietal layer. There's pressure in there pushing against the lungs. So there's pressure inside the lungs pushing out, and there's pressure outside the lungs pushing in. And we call the outside pressure the intrapleural pressure. That's because it's between the two pleura. So it's pushing in, and the pressure in the lungs is pushing out. Now, the pressure in the lungs always wins. The only thing that the benefit of the intrapleural, the goopy pressure, we'll just call it goopy so we keep an idea, it's the serous layers. The reason that is pushing against the lungs is to create tension in the lungs. So it's easier for them to inflate and deflate. So our pressure inside the lung, when we take a breath, we suck in air. Now, how do we suck in air? Well, when we enlarge our lungs, when our rib cage rises and our chest expands, our lungs go with them, and the space inside the lungs increases. And since there's more space there, and we haven't sucked any air in yet, we increase the space, the pressure drops, and air rushes in. And then we can contract the chest, we just push that air out. So it's all about air movement in and out based on the outside air pressure. Now, that'll make more sense here in a second. Let me see what there's another comment here. Let's see, exam 4 is open and 5 is going to open up. 5 won't open up until I get done with the content on the immune system. And the final, yeah, I'd like to, the suggestion was made that we do the final exam review on Wednesday afternoon. That works for me. If it works for you, let me know. Remember that even if it doesn't work for you, I'll still have it recorded for you, so you'll get everything that way. Okay, now let's move on to something a little more interesting here. Okay. Remember that the lungs always want to collapse. The lungs want to shrink down as far as possible. The lungs are going to shrink. Hang on a second, I got another comment. Okay. Okay, good. You're welcome. Now let's get back to this. Okay. The lungs are elastic. Lots of elastic tissue surrounding each of the alveoli. So they want to assume the smallest space possible. The fluid that lines the inside of the lungs is pulling is drawing the lungs in too. So our lungs always want to get small. The chest wall, though, is pulling our lungs out. So our lungs want to shrink automatically. The chest wall wants to expand. We also have the serous fluid pushing in on the lungs too. Okay, now let's get past this. How do we keep our lungs inflated? Because there is a condition known as collapsed lung that you may encounter. If the pressure inside the lung becomes equal to the pressure in the inner pleural, in the space, that pleural cavity, then the lung collapses. See, our lungs are normally stay inflated because, the pressure outside the lungs is always less than inside. No matter how, even if the lungs relax and get very small, the pressure is still greater than what's in the inner pleural space. But what happens if you get a penetrating injury right into the side of the chest that penetrates the lung and the pleural space? The air pressure is equalized and the lung will deflate. The lung will collapse in here. Okay. And that occurs, you have a penetrating injury to the chest wall, the thoracic cavity, and that's not uncommon. To have your, the lung will collapse. Okay, let's move on. Breathing, pulmonary ventilation, not the ugly term, cellular respiration. Remember cellular respiration, the Krebs cycle, other nonsense. Okay, pulmonary ventilation is inspiration, air going into the lungs, and expiration, gases, because it's gases going in and gases going out, leave the lungs. Inspiration and expiration. Inspiration, caused by the intercostal muscles contracting, raising the ribs, and the diaphragm dropping. So when the diaphragm drops and the intercostal muscles contract, the ribs rise, the lungs are glued to the inside of the chest wall, and the lungs expand. The volume of air inside the lungs, the volume inside the lungs expands. And there's a dramatic drop in pressure inside the lungs. It's 1 millimeter. That's all it takes. 1 millimeter of mercury pressure. We drop below the, if the outside air pressure is 760 millimeters of mercury, which it probably is, which is what it is right here, 759 is all we need. We drop only 1 millimeter. That's like saying your body temperature is 98.6 and drops to 98.5, or 98.6 it goes to 98.7. It's almost not even worth noting. But what happens is when we increase the volume of the lungs, the air pressure of the air pressure of the amount of air that's already in the lungs lowers. You have more space, so air rushes in. And all it takes is 1 millimeter difference. Your lungs get bigger. Maybe they double in size, I don't know, but the amount of air that was there has a whole lot more space to run around in. A whole lot more space for those air molecules to bounce around in than they did before. And for a split second, the pressure in the lungs drops by 1 millimeter. And that's all it takes for air to rush in from the outside. And breathing out, the ribs relax, they come down, the diaphragm comes up into its relaxed position, and the pressure inside the lungs rises to 1 millimeter above air pressure. It goes from 760 to 761, and that's all it takes for the air to equalize with it to go out. 1 millimeter difference. A drop of 1 millimeter in pressure causes us to breathe in. An increase of 1 millimeter causes us to breathe out. That's all it takes. And we gain that by increasing the size of the lungs or decreasing the size of the lungs. The pressure will rise when the lungs shrink. When the lungs get smaller, the pressure goes up. I mean, consider this balloon. Okay, let me. If I take this balloon, let me bring it up to the big screen here. Okay, this is a balloon, in case you weren't certain what it is. Now, if I start squeezing this balloon, what's going to happen to it? Is the pressure rising? Okay, if I start compressing the balloon underneath the camera, there we go. The pressure goes up. I'm decreasing the volume of the balloon. The pressure goes up. So our lungs do the same thing. When our lungs contract, it raises the pressure inside. When our intercostal muscles relax and the ribs drop and the diaphragm comes up, the volume inside the lungs is going to, the volume of the lungs is shrinking. They're getting like this. And if I squeeze this enough, it's going to pop. Okay. So now, I don't want to do that for a long time. Our lungs aren't going to pop like that under normal conditions. Theoretically possible under extreme conditions, you know. However, very extreme, very unusual conditions. However, that's the whole basis behind it. When our lungs relax, when the muscles relax and the lungs shrink back down, the pressure inside the lungs rises just enough to push the air back out. So when I shrink my lungs, when I go to relax and my diaphragm comes up and my intercostal muscles relax and the ribs drop and the volume, the space inside the lungs starts shrinking, the air inside there, the pressure rises because smaller spaces have higher pressures. The more pressure, the smaller the space, the greater the pressure went up. What happened when I squeezed the balloon? It popped because I raised the pressure inside the balloon. And the more the volume drops, the greater the pressure goes up. Now in our lungs don't pop because we can let the air out. And it only takes a millimeter rise in air pressure to force the air out to the outside air. Because remember, we're talking 760 millimeters is air pressure. A drop by 1 millimeter causes us to suck in air. A rise in 1 millimeter causes us to blow it out. Now, how did we get the drop in air pressure? Well, we raise our lungs, we raise our ribs, we drop our diaphragm, our lungs go along with that, and just for a very short period of time, the volume in the lungs has increased drastically. The amount of air that's in there now has a whole lot more space to bounce around in, and the pressure drops just enough to be slightly less than outside, and that causes air wants to equalize. It goes from the high pressure to the lower pressure, just like diffusion, and air rushes in. And then when we squeeze our lungs, we force it out. And that's how we breathe out. So hopefully we don't pop like that. So yeah, that would be bad. So on the other hand, you probably wouldn't care after that. So anyway, so that's the whole basis of breathing that we take in. You know, we raise pressure, we lower pressure. Now, we have resistance in our airways. Our bronchi cause a great deal of resistance in here. But that's okay. You know, whatever resistance you're doing is whatever the normal resistance is, the pushback in here. However, if resistance to airflow rises, it's just like what we have with resistance in the blood vessels. We have to work harder to breathe. If our bronchi start narrowing more than they should, then we have problems breathing. And remember that our bronchi are surrounded by smooth muscle, and the smooth muscle can constrict the airway. We can, you know, that vasoconstriction we talked about in blood vessels, we can have bronchoconstriction here. Same type of constriction. Smooth muscle contracts and we narrow the airway. A patient that has asthma involves a narrowing of the airways, a narrowing of the bronchi. A person who has an asthma attack and doesn't have their rescue inhaler is going to suffer a great deal of difficulty in breathing because the airways have gone from this, you know, wide open to extremely tiny, and they can't ventilate and they can't get air exchange to go through here. Most of your rescue inhalers are going to contain epinephrine, which causes the smooth muscle to relax. Because see, it's the smooth muscle that's the problem. And we know that epinephrine and norepinephrine are going to affect smooth muscle. We can get vasodilation, we can get vasoconstriction. Norepinephrine causes what? Vasoconstriction of the smooth muscle in the arterioles. Epinephrine causes relaxation of the smooth muscle in the airways. You know, these are, if you remember back to AP1 and we talked about the sympathetic and parasympathetic nervous system, we know that the sympathetic system uses epinephrine and norepinephrine as its neurotransmitters. Epinephrine in some places is excitatory, in other places it's inhibitory. This is one of those inhibitory places where it causes things to relax. Normally we think of epinephrine as exciting the heart, which it does. But then we think of acetylcholine as exciting skeletal muscle, which it does, but it relaxes the heart. Here, epinephrine, like we would have in an EpiPen or in a rescue inhaler, is going to cause the smooth muscle around the airways to relax and open up. So a person who's having an asthma attack would use their rescue inhaler to get their airway to open up. Okay. Now, one of the problems we have with our lungs is that the alveoli are covered with water, because everything that we breathe in has to be dissolved in water first before we can breathe it in or breathe it out. Oxygen has to dissolve in water on the surface, on the inside surface of the alveoli, so it can diffuse across into the capillary and into the red cells. CO2 is in solution. It has to come out into that water layer so that we can breathe out the CO2. So we keep the alveoli lined in water. But imagine 2 pieces of single ply wet toilet paper, the really cheap stuff like they use here. You know, oh, did I say that well? So, okay. The cheap stuff they use in some places. Okay. So imagine single ply wet toilet paper. We know how it sticks together. Now that is super thick compared to the thickness of 2 cell membranes, but it's the same thing. Wet surfaces like to adhere to each other. Now we don't want that to occur in our lungs. So we coat our lungs with something called surfactant. It's like soap. It's like dishwashing liquid. If you've ever seen what dishwashing liquid does to grease or oil in a pan, it breaks up the grease and oil into little tiny pieces. It breaks the surface tension of the oil so you can get the pan clean. Surfactant keeps the surface of the alveoli from sticking together. We don't want it to stick together. We want it to be, you know, 1 cell layer thick on all 6 million or however many million, I forget the number, millions of alveoli. That's one of those little factoids that, you don't really need to remember in reality. So how many alveoli do you have, It's like, well, there's 1 million nephrons in each kidney, there's another little factoid that, might show up on a test, might not. I don't remember if it does or not, but it's, when was the last time somebody came up and asked me, how many, how about your 1 million nephrons? How are they doing today? I don't know, Anyway, lung compliance. Compliance. This is the ability of the lungs to expand and relax. Lung compliance determines how well we can breathe. It how well do our lung tissues work? Now, the problem we have with compliance is that things affect it. The elasticity around the alveoli can be destroyed by the disease emphysema. Emphysema, 85% of all emphysema cases result from tobacco smoke. And if you have if you want to make it really interesting, take a coal miner that smokes and moonlights in a job installing asbestos in naval vessels. He's got 3 strikes against him right there, because all 3, his odds of developing emphysema are probably in the high 99% range. What emphysema does is it destroys the elasticity of the alveoli by attacking the smooth muscle. And so our little bubbles are elastic. They expand when our lung expands, and they relax when our lung relaxes. But with emphysema, the alveoli expand and never let go. They trap air. And the more air they trap, the less you can get air exchange. You get bigger and bigger. And one of the consequences of emphysema is this what we call a barrel chest, because the chest gets bigger and larger because the lungs have these massive bubbles sticking out on them of surface tissue, trapped air, to the point that in some cases, lung reduction surgery is called on to cut away the trapped air areas. So pretty extreme procedure. They do it all the time over in Vanderbilt. So, or they do a lung transplant, one or the other. So, okay. So we pay attention to the elasticity of the chest wall. They say distensibility, meaning will it expand and contract. We also pay attention to do the alveoli stick together. Is the surface tension holding them together, or is it enough so that the alveoli can expand individually? Things that affect compliance. Well, I mentioned destruction of the elastic fibers around the alveoli. But what if you have scar tissue for some reason? Maybe your patient had tuberculosis. Maybe your patient has some sort of occupational disease. There used to be one where people that worked in the clothing factories would inhale lots of cotton fibers, and the cotton fibers would accumulate in the lungs and start interfering, restricting the airways and filling up the alveoli. So not so much anymore, because we don't have as many fabric factories, cotton factories and stuff like that in the US. But across the South, it used to be a big thing up until probably 1970. So now, mucus. Believe it or not, plain ordinary mucus is going to get in the way of breathing. The more mucus that someone produces, mucus increases the thickness of the membrane for air exchange. Pneumonia is a very serious condition. We don't think much about it, but about pneumonia. But one thing that COVID did was remind us that pneumonia kills people, and it works by generating a lot of mucus that accumulates on the inside of the alveoli, making the membrane thicker. Now, oxygen can't diffuse through thick membranes. It likes a very, like 0.05 micron or some very tiny membrane to get across. With a layer of goopy mucus there, it's really hard for oxygen to get in and CO2 to get out. So that's why pneumonia is a very dangerous condition. So your patient with cystic fibrosis is a genetic disorder caused by, and it causes, it's one of those recessive traits that you have to get from both parents to have it. And what it does is it increases the amount of mucus produced in the lungs and the airway. And so your patient with cystic fibrosis is always fighting for air, always trying to overcome the layer of mucus that's forming inside their bronchi and around their alveoli. And it used to be that your patient with cystic fibrosis would die when they were about 28 years old. Yeah. Hey, we got a warm, dark, moist environment with lots of mucus inside the lungs. Let's grow some bacteria and kill the host. Yeah, well, now the average age lifespan of cystic fibrosis patient has increased to about 55. So it's getting there. So the other thing that this mucus does, I'll digress for a second. It also accumulates around the pancreatic duct, making it difficult to process proteins. Many of your cystic fibrosis patients have difficulty reaching a normal adult stature because of the lack of protein. So it isn't just, cystic fibrosis isn't just a breathing problem, that's the big one, but it's also getting enough protein absorption in the duodenum. So anyway, other things, not enough surfactant. Not enough surfactant means the alveoli stick together, and if our intercostal muscles can't contract, or if our diaphragm can't contract, all of these are going to interfere with the ability to get good air exchange here. So now that is inspiration and exhalation. Now, pulmonary ventilation, that's what I was alluding to earlier about the pressures. This pulmonary ventilation is mechanical. This is a mechanical process dealing totally on volume changes. Now we're going to get into a 3 or 4 laws that you'll need to remember. That will I guarantee you will absolutely show up on exam 5 and on the final. So pulmonary ventilation is driven by these physical laws that about it. Now, now to understand the movement of air, let's talk about how much air we're in here. Sitting here right now, breathing in and out. The amount of air with each breath you're moving out is about 1/2 liter, 500 mils. That's called the tidal volume. Circle that, put a star around it. You might need to remember that. The tidal volume, just resting air movement, just breathing in, breathing out, about 1/2 liter. Now, if we were to measure how much air you can suck in after you take a breath, let it out, and then suck in as much air as you can, we call that the inspiratory reserve volume. That's about 3,200 mils. That's a little over 3 liters of air. That's how much can we fill up? Now, what we have next is how much can we blow out? So you've had a tidal volume movement of air in and out, and then after that, you blow out as much as you can. And that's about 1 liter or so. What do you have left? Well, we have the residual volume. That's what we find in the badly named dead airspace. It's the air that's in your trachea, it's in your bronchi, it's in your nose, it's in the nasopharynx, the oropharynx. You know, this is air that hasn't gotten down to the alveoli yet. This is the air that's left over. Another 1,200 mils. If you've been keeping score, we have about 6,000 milliliters of air, or cubic centimeters. You know, magic number is 6,000. The vital capacity is 4,800. So the residual volume down there in gray is the air that it's either on its way down to the lungs or on its way back out. You know, it's headed back out to our mouth and nose to breathe out. So that's the air that we're not using. The expiratory reserve volume is how much air is in our lungs we can blow out. The tidal volume is what we're doing back and forth right now, and the inspiratory volume is how much more we could suck in as necessary. Because the average lung capacity of the average vital capacity for an individual is about 4,800 mils, almost 5 liters of air. Total volume of the lungs are about 6 liters, 6,000. So. Now here are the laws. We have Boyle's law, Dalton's law, Henry's law, the Bohr effect, the chloride shift, and the Haldane effect. So, and let's go over these and explain what they do. Boyle's law simply says that volume and pressure are inversely related. When pressure rises, when pressure increases, volume drops. When I was squeezing the balloon, when I squeeze the balloon and I compress the balloon, I'm reducing the volume. When I reduce the volume, I'm not going to pop it, don't worry. So I didn't mean to do that. So I put it down. So okay. When the volume shrinks, pressure goes up. As I squeezed the balloon, pressure went up and it popped. When volume expands, pressure drops. You know, I mean, example, if there was no furniture in the room at all, just nothing in here, and you were all blindfolded, and I said, just walk around and try to bump into each other. You couldn't hear anything, couldn't see anything, just walk around, see if you can bump into each other. You know, you might go for quite a while before you run into each other, okay? But instead, let's all, well, I'm not, but everybody go back into the small room back there, back into the office. Now, that office is about 1/10 the size of this classroom. Now you're all walking around in there. How often are you going to run into each other there?
Very often.
Exactly, because the volume was cut by 90%. Now it's a much smaller room. You know, pressure is nothing more than molecules of air bouncing against the walls of the lungs, or a cylinder, or a big room like this. If you all are air molecules, you know, you're bouncing into each other occasionally. In there, you're going to be hitting the other all the time. The smaller the space is, the higher the pressure is going to be. So if we increase the volume of our lungs, the pressure drops. If we decrease the volume of our lungs, the pressure rises. So when our lungs expand, the pressure in the lungs drop. Air rushes in, because air will always go from high pressure to low pressure. So our lungs satisfy Boyle's law. All you got to do, remember what Boyle's law is, volume and pressure are inversely related. When pressure drops, volume goes up. When pressure rises, volume goes down. And that's how our lungs satisfy the air movement. So now Dalton's law is partial pressure. Now think about this for a second. The air pressure in here is 760 millimeters of mercury, even though it says 752 there. The air we're breathing is a mixture of oxygen and nitrogen. It's about 20% oxygen and 80% nitrogen. That makes it a mixture. If we add the partial pressure exerted by oxygen to the partial pressure exerted by nitrogen, we come up with 760, more or less. So 760 millimeters of mercury. If you take 20% of that, 20% of 760 is about 160 millimeters. That's what oxygen does. 80% of 760 is about 600, more or less. So if you add the two pressures together, you get the total air pressure. This is all that Dalton's law says, is that all the gases together give you your final, your overall pressure. And we don't, right now, we don't care about the CO2 and the carbon monoxide and the methane and all the other little trace gases. The two big ones are oxygen and nitrogen. So the pressure of those two together give us the ultimate air pressure. I mean, remember, what we're breathing in is 80% nitrogen, but that 20% is enough for us to survive. So the Dalton's law, you just add up all the air pressure, all the gas pressures. Henry's law. Henry's law says that gases will dissolve in proportion to their pressure. And carbon dioxide is more likely, 20 times more likely to dissolve in plasma than oxygen. So anyway, Henry's law, gases dissolve in liquids according to their partial pressure. Why do we care? Well, what happens when we generate carbon dioxide? What happens to our blood? What happens to our blood when we generate carbon dioxide at the Krebs cycle? CO2 combines with water to make what? Okay. Okay. How about carbonic acid?
Yep, that's the one.
Yep, carbon dioxide and plasma form carbonic acid. What happens to our blood when we start generating more carbonic acid? Our blood becomes more acidic, right? And what do we do when our blood becomes more acidic? I've been saying this since AP1. We breathe faster.
It's Monday.
I know it's Monday. Why am I talking? Why am I talking about a hard topic on a Monday? What is wrong with me? I've been saying since AP1 that the driver for breathing faster is not the need for oxygen, but because we generate carbon dioxide, which forms carbonic acid and lowers our blood pH, and we breathe faster, right?
Yes.
Right. Thank you.
Yes.
Thank you. Yes. Okay. Now, oxygen doesn't do that. Oxygen gets picked up by the red cells, but CO2 can dissolve in the plasma too. And that's why CO2 controls the rate of breathing for us. So, because of its solubility in here. Henry's law says gases dissolve in proportion to their partial pressure, but the ringer is CO2, which has its own unique solubility in water. Okay. The Bohr effect. The Bohr effect is sort of like, oh, here's a nice freebie for you on when you're dealing with the Bohr effect, because we generate carbon dioxide, we make our blood more acidic, but surprise, when we get more acidic, our red cells release more oxygen. So just when we need more oxygen, we get it without having to do it. Breathing faster doesn't bring in more oxygen. We breathe faster because our pH has dropped, but when our pH drops, the red cells are going to easily let go more oxygen just when we might need it. This is the Bohr effect. The more CO2 we generate, the more oxygen we're going to release from the red cells. The more acidic we are, the more likely we are to release more oxygen just when we need it. This is the Bohr effect. And the more acidic, as we get more and more acidic, we release more and more oxygen. And there's a very famous and very difficult to understand curve here that it's not intuitively obvious here, but we see that we shift with as the CO2 levels are going to shift to the right, as the red line there, the high levels of CO2 in the blood, we're going to be releasing, if we look at the chart down at the line across the bottom there, the higher the CO2, as the red line rises, the amount of, if we track the red line straight down to the bottom graph, we can see as the red line goes up, meaning more CO2, the more oxygen we're going to be releasing down at the bottom. So that's the Bohr effect. And so it allows us to dump more oxygen out of the blood. Simply, so we aren't, CO2 drives us. Remember, I've been saying since AP1 that carbon dioxide drives our breathing rate. It also is throwing in more oxygen for us too, by making our blood more acidic and allowing this Bohr shift or Bohr effect to take place. Now the chloride shift, this is something pretty out there. Red cells are going to pick up carbon dioxide. It's going to form carbonic acid to stay balanced. Because carbonic acid is you're going to have the carbonic acid being absorbed by the red cells. So, and bicarbonate goes into, so carbonic acid is formed with CO2 and water. Bicarbonate is the balance. Bicarbonate is the buffer to neutralize the acid. So when we form carbonic acid, bicarbonate diffuses into the plasma to neutralize the acid. Well, the red cells don't like that. The red cells don't like to lose their bicarbonate. They're giving up the bicarbonate. Bicarbonate is our buffer. They're giving that up. So the chloride shift is we've got to neutralize the loss of the bicarbonate. So let's send the chlorine into the red cell. What the chloride shift essentially is the red, when the red cell gives up bicarbonate to neutralize the carbonic acid, chlorine goes in. There's no easy explanation on that one. I'm sorry. And your last one here is called the Haldane effect. This is one of those that will show up on a test question and it'll seem like, what a goofy answer, and you'll think, which, you'll have all these great answers there, and then you'll want to see the one that says the Haldane effect. Like, what is the Haldane effect? Well, the Haldane goes hand in hand with Bohr. Remember, the Bohr effect says that as more CO2 is released, as more CO2 is generated, red cells release more oxygen. Well, the counterpart to this is the more oxygen and hemoglobin that's being released by the red cells, the more carbon dioxide they can carry. So the Bohr effect says the more CO2 you have, the more oxygen you're going to release from the red cells. The Haldane effect says the more oxygen you release, the more CO2 you can carry. So is somebody at someone had to discover all this stuff too. Okay. Anyway, those are the laws that you need to remember. You may not have to remember them very long, but you need to remember them at least for the next week and a half or so.
On the chloride shift, you said when the red cells give up carbonic acid, bicarbonate goes in and what?
The red cells are going to absorb, the red cells are going to give up bicarbonate. So the bicarbonate has a negative charge to it, and the chlorine has a negative charge to it. So when the red cells give up the negative bicarbonate, chloride has to go in to keep the red cell balanced, because we're putting the bicarbonate out into the plasma to neutralize the carbonic acid. So, and the red cell has to stay balanced, so it sucks up the chlorine. Chlorine finally gets to do something. Not much, but it does get to do something. Most of the time, it's just watching. Okay, atmospheric air. Atmospheric air is 21% oxygen, just say 20%, 80% nitrogen, more or less. You got a bunch of trace gases there. You got carbon dioxide, 0.04%. That's not very much, but that's what's in the air we're breathing in and breathing out right now. One of the classic questions is if you're administering rescue breathing to somebody, artificial respiration, how can that be working if you're breathing out carbon dioxide? Well, you're not breathing out that much, and there's still plenty of oxygen left. If you notice that the expired air there, the third bullet down, it's still 16% oxygen. We only use about 5% of the oxygen in the air on every breath. And yes, it's about 4.5% CO2, but it's still got lots and lots of oxygen available there. What gets down to the lungs? What gets down to the alveoli? About 14% oxygen. So we go from 21% to 14%, and we have 5% CO2 at the alveoli. Now, why are we so low at the alveoli? Because oxygen is always diffusing across the membrane. Why is CO2 so high at the alveoli? Because it's always diffusing across the membrane. CO2 is always coming out, oxygen's always coming in. Fortunately, as long as we're breathing, we're maintaining this higher concentration here. Okay. I just said that already, so, okay, now. Numbers. Partial pressures of oxygen. You ever had a pulse oximeter on your finger? Most of us had at one point or another. I know you probably just had the other day. So, and a friend of mine just recently recovered from COVID, and he was in intensive care for 2 months. And it was really touch and go for him. And he had it, his wife had it, his son had it. In fact, his other son died from pneumonia. So, and he had the pulse oximeter on there, and he said that he would work very hard to keep his numbers higher than 90%, so the alarms wouldn't go off, because if he dipped into the 80% saturation levels, then the alarms would go off and everybody would come rushing in to see if he was still alive. So it also would wake him up at night too, because he had to learn how to sleep without setting off the alarm. So anyway, pressure in blood. In a return flow blood, the pressure oxygen level in blood is 40 millimeters of mercury pressure. In the alveoli, it's 100. So we have a very high saturation level in our alveoli and a pretty low saturation level in our venous return. What this does is that what this shows is that the oxygen level goes into our blood very rapidly. there's such a, the difference between 40 and 104, the gradient is so steep that oxygen always diffuses from the highest concentration into the lowest concentration rapidly. A quarter of a second, it says here. So. Now here's something that I've been mentioning this a lot previously about red cells and stuff like that. We know that oxygen is carried by the red cells. Only about 20% of the oxygen carried in a red cell is unloaded in one pass through the body. About 20 seconds or so it takes to go through the body and through the systemic circulation, and it only gives up about 20%. Now, that means that we have 80% left as our reserve. That's why everybody, I'm gonna change this question. On test 3, I had a question, which chambers of the heart contain oxygenated blood? The correct answer was all of them, because even on the right side, it's 80% saturated.
That is a bad question.
I know it's a bad question. Nobody gets it right. No one has got that right.
Well, I hope you marked it right on.
I did, actually. I went back and changed it. So everybody, yes, it was a terrible question. And I changed it on everybody that got it wrong, which is almost everyone. So, of course, when I asked the faculty, they all said, "Oh, well, all of them do," So, but they're a biased audience. So,
Yeah.
So,
And you do this for a living.
yeah, I do. Don't I?
You could talk about the heart in your sleep.
I probably could. So, the point though was that every chamber is oxygenated. 80% on the left-hand side, 100% on the right. 80% on the right-hand side, 100% on the left-hand side. It was a tricky question. That's about as tricky as I get. So, and because I had this hope that maybe somebody would take the time to read the question and read into it, but nobody did. So you all got credit for it. Anyway, the point though is that all the blood is oxygenated. 80% on the right side, 100% on the left side, because we only lose 20% per pass through the body. That 80% is our reserve. So when you go climb those stairs, you have more oxygen to draw on if you need it. If you run to the parking lot, you have more oxygen to draw on if you need it. And if we do use up more CO2, then the Bohr shift's going to come and help us by allowing the red cells to give up more oxygen if we get more acidic. And it's also going to let us carry more CO2 to the lungs with the Haldane effect. So those two work side by side here to get rid of to give us more oxygen when we need it, and to give us CO2. Remember, 80% is what we're only using 20% on right now you're using 20% every pass. But if you got up and decided to run up and down the hall for whatever reason, I don't know, and you were burning more glucose, you would generate more CO2, and that would cause you to give up that extra oxygen that you need. So I alluded to this earlier. The thickness of the membrane is really, really important to us. The thickness of the alveoli is somewhere between a 0.5 to 1 micrometers. That's a thousandth of a meter, or 10,000. It's incredibly tiny, okay? Total membrane surface area is about 60 square meters. Now, that's 40 times the amount of skin that we have on our bodies. So something about the size of this classroom, 60 square meters. I haven't measured it. Maybe it's 2 classrooms. I'll have to measure it one day and see. But it's a lot of space. That is the respiratory membrane for getting gas exchange across here. And it's all half a micrometer thick. So yeah, it's incredibly small. The problem occurs when we have pneumonia. The problem occurs if your patient is retaining fluid in the lungs. Pulmonary edema, where's that water going? It's filling up around the alveoli. It's increasing the thickness of the membrane. Oxygen doesn't do well when you get above about 1.5 micrometers. It can't diffuse very far. We like to keep those distances very, very short. And if we get thicker and thicker, it's harder to get those gases going back and forth. So emphysema, one of the things that emphysema does is it breaks down the walls of the alveoli. So we end up with less, not only are they not elastic, but the surface area shrinks too. Okay, now let's see. Now at the level of the tissues, we're dealing with the movement of the gases from the capillaries to the tissues and from the tissues into the capillaries. Oxygen levels in the blood is always going to be higher than in the tissues. Oxygen will always diffuse into the cells. The gradient is always higher from the blood to the cells. And CO2 is always higher in the tissues than in the blood, in the capillaries. So CO2 always diffuses out, oxygen always diffuses in. CO2 diffuses out, oxygen always diffuses in. So how do we get rid of our CO2? Well, most of it gets, we always say CO2 dissolves in the plasma to form carbonic acid. And yeah, that's true. It's enough to alter our blood pH, but that's only about 10%. 20% is carried in the red cells. You know, the hemoglobin will pick up about 20% of CO2. Remember, the red cells are still carrying a lot of 80% oxygen. Most of our carbon dioxide is carried as bicarbonate, HCO3, the negative side of sodium bicarbonate buffer. So we have 3 ways to get rid of the CO2. Plasma as carbonic acid, carbaminohemoglobin carried in the hemoglobin itself in the red cells, or as the bicarbonate ion. So our carbon dioxide so what will happen here is, so we're carrying, you know, the 70%, here comes our bicarbonate, HCO3. HCO3 being carried in the plasma, you know, when we get to the lungs, the bicarbonate moves back into the red cells and ends up forming carbonic acid. The carbonic acid is then split into carbon dioxide and water, and the CO2 then is released. So what's happening here? Here is our red cell right here. There's our red cell. There's our carbon dioxide coming from the cells. Carbon dioxide combines with water inside the cell, forms carbonic acid. We keep the hydrogen ion and we kick out the bicarbonate, and that's carried in the blood, in the plasma. There's that chloride shift I said earlier. So negative out, negative in. We get to the lungs. The bicarbonate goes back into this red cell. The chloride leaves. Bicarbonate combines with the hydrogens inside the red cell, forms carbonic acid, which is broken by this enzyme and releases the CO2. This is what's going on back and forth. We carry most of our CO2 in the form of the bicarbonate. That's your answer, by the way. Most of the CO2 shows up as in the bicarbonate. So what controls breathing? The medulla. There is an inspiratory center in the medulla that sets our breathing pace at about 15 times a minute. The inspiratory center tells us to take a breath. We suck in air and then it stops. So we about 15 times a minute is our breathing rate. Every time we suck in air, it'll tell us to suck in air, and then when we go exhale, it shuts down and starts up again. So it starts and stops and starts and stops. Problems: hyperventilation. What happens in hyperventilation? We breathe rapidly. We breathe so rapidly that we blow all the CO2 out. If we hyperventilate, we blow away all of our CO2. And that's not a good thing, because if we blow off all of our CO2, we start becoming basic. The other side of this is hypoventilation. You don't breathe, you breathe slowly. Hypoventilation allows you to become more acidic. You have a very slow breathing rate. Hypoventilation tells you to makes you more acidic. Because you're retaining CO2. You can hypoventilate in here because you have an obstructed airway. You have damage to the medulla oblongata. Something's going on here. Why do you hypoventilate? Because your CO2 levels are low. If your CO2 levels are low, you're alkaline, so you slow down your breathing to retain more CO2. Now, but then if we're hypoventilating normally and we're retaining CO2, we're going to become more acidic. So our response to this acidosis, of course, is to breathe faster. Okay, let's move on. What happens to us if we go up into high elevation? What if we took a field trip this afternoon to, let's say, that's not high enough. No, it's like double that. Sorry. I mean, actually, I tried that. I took a pulse oximeter up to Mount LeConte one time and didn't notice a thing. And it's 6,000 feet. I didn't notice. Yeah. So. Yes, I'm a geek even when I hike. So if we go to someplace at high altitude, remember at every 10,000 feet, our oxygen levels are cut 50%. So the pressure of oxygen at 10,000 feet is only 80 millimeters, not 160. We have less available oxygen. We have to produce more red cells so we can carry that less oxygen around. If our oxygen levels are low, we're going to generate red cells. If we have less oxygen available and more CO2, we're going to trigger, that's also going to be the driver, to trigger erythropoietin to release and say, let's make more red cells. We acclimatize, I got that word out right, in just a couple days, I mean, you will notice the first time you try to do anything of any strenuous activity, even something as simple as trying to run across the street at 10,000 feet, you're going to be very short of breath. But in a couple of days, you'll be fine. You will have acclimated to the lower oxygen levels. So here's something where you'd run across the street and not notice it at all. There, at 10,000 feet, where the amount of oxygen in the air is only 80%, not 160, you're going to suffer. You're not going to win that race with the car coming down the road. So you have to, Anyway. Okay, here we get into the good stuff, the diseases, the things that go wrong. COPD, you hear a lot about COPD. Chronic obstructive pulmonary disease, we're in the top 10 in the US for COPD cases here. Emphysema and chronic bronchitis. In both cases, you have difficulty getting air out of the lungs. You can't breathe out as well as you could before. COPD is going to destroy the elasticity of the alveoli. Smoking is the cause of 85% of all cases of COPD. Now, other cases can include exposure to occupational chemicals, secondhand smoke, really rare, but it can occur. Industrial chemicals, coal mining, mining in general can all affect, can be triggers for this. Chronic bronchitis, inflammation of the bronchi, which keeps them narrowed. It isn't like the bronchitis you get and you're over it in a couple days. So asthma is usually not considered part of COPD. Lots of people have asthma. Asthma is a acute condition. Remember, chronic obstructive pulmonary disease is a chronic condition. It's long-term acute inflammation of the airways. The bronchi become inflamed and enlarge, narrowing the airway. You also get a lot of mucus that forms in here with asthma. Asthma can be controlled very easily with medications, with the right inhaler, various types of medications for that. Asthma is usually not considered COPD. As I said, 85% of all cases are caused by smoking. Now, the symptoms you see, clubbing of the fingertips, is up here on the screen there, is a classic sign. Notice how the fingertips are clubbed. You're reducing the blood supply going out to the extremities. So they're going to enlarge like that to try and increase the flow as best they can. The barrel chest, because the lungs have inflated and haven't deflated. So a person with an enlarged chest like that, they breathe through their lips like that, because it's easier to control the muscles here to suck in air like that. Pursed lipped breathing, that is a classic sign there. Cyanosis. Blue tint to the tissues, particularly in the nail. Well, the nail beds are the giveaway. Doesn't matter the skin color. The nail beds are always going to be the giveaway because they're always pink because they're highly oxygenated. If they have a cyanotic tint, a blue tint, it means that the oxygen saturation levels are low. So you always look at the nail beds, or examine mucous membranes in them. Nail beds are easiest. Everybody has nail beds. Almost everybody has nail beds. There's always an exception, but almost everybody has nail beds. Look at them, and they'll tell you cyanosis. Cyanosis because of the reduced oxygen capacity. They appear blue because there is less oxygen in the hemoglobin. Remember, hemoglobin is bright red when it's fully saturated, and it's just dark red when it's partially saturated. Venous blood is dark red. Remember, venous blood is 80% saturated. You've only lost 20% on one pass. Venous blood, it's why veins look blue in your skin. It's why the nail beds turn blue or the lips turn blue when with cyanosis, because you're not getting enough oxygen into the hemoglobin. So, and the reason that they purse lip breathe like that is because they can't get their lungs to expand, because their lungs are already inflated with all this tissue on there. Now, chronic bronchitis. chronic mucus, chronic inflammation. The airways are obstructed, reducing the amount of air actually getting to the alveoli. Your patient has chronic infections you have to deal with in here. Again, what's the cause of it? Well, occupational exposure, smoking, things like that. If they don't get emphysema, they're probably going to get chronic bronchitis, but there's a whole lot of other things that can trigger this too. So, treatment. Treatment depends on how they breathe. We describe two types of patients. The pink puffers. The pink puffers, their skin looks normal. Their nail beds look pink. They look normal. They're very thin. However, the pink puffer is going to be breathing rapidly. They use a lot of effort to breathe. They're thin because they're burning up most of their glucose just to get their muscles to function to have ventilation. They look reasonably healthy. Cyanosis is not an indicator on your pink puffer. And again, it doesn't matter the skin color. The nail beds are pink, but they're very thin. The individual is very thin. You may want to suspect something going on here with COPD. The blue bloater, your patient is larger, nicer. They're stocky. Okay, they have cyanosis because they're not oxygenating the hemoglobin properly. Again, look at the skin, look at the nail beds. Nail beds are never wrong. So, because they're always, this is where you're close enough to the surface of the skin to actually, you can tell if the blood is being oxygenated properly. So these are the blue bloaters. They're larger. They have a bluish tint to them. Not like the blue people up in Kentucky, but just a little cyanosis on the lips, the nail beds, the skin itself. So treatment. Bronchodilators, open up the airways. This is long-term. Steroids, corticosteroids, lots of oxygen. Lung volume reduction. This is where they have the inflated lungs have to be cut out. I think I had a picture here. Or not, no, I don't. Okay. Lung cancer, you're going to encounter this also if you get involved with any kind of respiratory care. 1/3 of all cancers are caused by lung cancer. Most were smokers. The three big cases are, and this is not a testable question, so this is factoid. Squamous cell, adenocarcinoma, and small cell, they're all about the same percent in here. A person with lung cancer doesn't necessarily have to die because there are 4 stages of every cancer. Even stage 4, where the cancer has metastasized somewhere else, doesn't have to be fatal. Stage 4 is often misinterpreted as death sentence because it means it has spread somewhere else. It doesn't necessarily have to kill your patient if it's still caught in time. So now, lung cancers. Here we have a PET scan. PET scans are great for detecting these types of cancers. Here we have the PET scan showing the cancers, the tumors where the arrows are, and also a cancer growing in the lymph nodes, under the left arm. But then what does it look? Obviously, they didn't survive. Look at the lungs on the pathology of the lungs. This is what a lung looks like from the outside with lung cancer, the one on the left. And you can see the large tumors in there. Lung cancer kills your patient because in 2 ways. It fills up the available air spaces for gas exchange, or the tumor grows into one of the blood vessels and eats away, and the blood vessel ruptures and they die from bleeding out. So it's not a pleasant way to die. So, anyway. Okay, and that is respiratory. So, and with 3 minutes to go, I'm not going to start the new topic. So, oh, I can. You want me to start?
I'm about to be on myself.
Hmm? Yeah, I'll take. Okay, let me see if there's any. Are there any questions on anything? Okay, then I'm going to get us out of here. Wednesday, we will go into the immune system and plan on the review at 1 o'clock on Wednesday afternoon. If you can't make it, I'm going to record it. So, I'll see you all later.